Hello everyone and welcome back to the AI Research Roundup. I'm your host Alex, and today we're diving into some interesting new work in the world of 3D rendering. We're looking at a paper called 3D-GUT Enabling Distorted Cameras and Secondary Rays in Gaussian Splatting. So, 3D Gaussian Splatting, or 3DGS, is known for being really efficient at creating these detailed 3D scenes you can render in real time. But it has limitations. It typically only works well with standard, ideal pinhole cameras and doesn't handle complex lighting effects like reflections or refractions. This paper proposes a new method called 3DGUT, which stands for 3D Gaussian Unscented Transform. The core idea is to replace part of the standard 3DGS process with this unscented transform. This lets it handle, well, distorted cameras. Think fisheye lenses or even rolling shutter effects, while keeping things fast. Plus, it adds support for those secondary lighting effects, like reflections, which is pretty cool. Okay, so let's look at Figure 1 here. It really shows off what 3DGUT can do. On the left, you can see comparisons using distorted camera views, like those fisheye examples. It shows that training with the original distorted views, using their method, gives better results compared to trying to use undistorted views first. And then on the right, this is where it gets interesting. They've added synthetic objects into a scene reconstructed with their model. You can see a shiny sphere showing reflections and a glass statue showing refractions. This highlights that ability to handle secondary effects we talked about. So building on how 3DGUT handles those distorted cameras, Figure 2 really shows the core mechanism. It compares different ways to project a 3D Gaussian particle onto the 2D image plane. The standard EWA method in the middle approximates things, which can cause errors with distortion. But the unscented transform, on the right, which is what 3DGUT uses, well, it uses a set of sigma points. These points get projected exactly, even through complex lens distortions, and then it reconstructs the 2D Gaussian. That's how it avoids the linearization issues. Okay, so related to how these Gaussians are handled, Figure 3 shows another important difference between standard 3DGS and this new 3DGUT method. It's about where the particle's contribution is actually evaluated. Standard 3DGS, shown on the left, projects the 3D Gaussian onto the 2D image plane first, and then evaluates its effect there. But 3DGUT, well, it evaluates the particle's response directly in 3D, finding the point of maximum response along the ray itself. This avoids having to backpropagate through that potentially complex camera projection function, and it aligns better with ray tracing approaches, which helps with those secondary effects. Moving on from how 3DGUT handles projection and evaluation. Figure 4 gives us a look at how it stacks up against other methods on a standard dataset, MIPNER F360. This isn't focusing on distortion or secondary rays specifically, but rather on the general novel view synthesis quality. You can see their method, labeled ours, compared to the ground truth and several others like the original 3DGS. The main thing here is that 3DGUT achieves really comparable visual quality to the established methods on this common benchmark. It shows that adding those new capabilities hasn't really hurt its performance on standard tasks. Right, so Table 1 here gives us the hard numbers behind those visual comparisons on MIPNER F360 and also the tanks and temples dataset. We're looking at standard quality metrics like PSNR and SSIM, where higher is better, LPIPS, where lower is better, and importantly, FPS, or frames per second for speed. Looking at the results, hours and hours, which represent 3DGUT, they achieve PSNR, SSIM, and LPIPS scores very close to the original 3DGS. For example, on MIPNER F360, PSNR is 27.26 for both, very similar to 3DGS, but well, check out the speed. 3DGUT runs at around 200 to 265 FPS on MIPNER F360. That's still really fast, but a bit slower than the original 3DGS, which hits 347 FPS. However, it's significantly faster than ray tracing methods like 3DGRT at 52 FPS, which can also handle complex cameras. So it confirms comparable quality to 3DGS on standard tasks, while keeping most of that real-time speed. So digging a bit deeper into those speed differences we saw in Table 1. Table 2 here breaks down the timings in milliseconds for each step on the MIPNERF 360 dataset. We have columns for things like pre-processing, sorting, and the actual rendering time. If you look at hours, our 3DGUT method, the total time is 3.77 milliseconds per frame, compared to 2.88 milliseconds for the original 3DGS. It looks like the main increases are in the pre-process and render stages. The Rs version, which handles ray tracing alignment, is a bit slower at 4.98 milliseconds, mostly due to a longer render time. But, well, look at 3DGRT, the ray tracing method. Its render time alone is over 19 milliseconds. So this breakdown confirms that while 3DGUT adds a little overhead compared to 3DGS, it's still way faster than ray tracing alternatives. Okay, so speaking of datasets with more complex cameras, Figure 6 shows a visual comparison on the Waymo dataset. This dataset is known for having camera distortions and rolling shutter effects. We see the ground truth image on the left, the result from 3DGRT, that ray tracing method, in the middle, and our 3DGUT method, the sorted version, on the right. Visually, well, the result from ours looks really quite close to both the ground truth and the 3DGRT result. It demonstrates that 3DGUT can handle these challenging camera types effectively, producing high-quality novel views that are comparable to ray tracing methods, but as we saw from the tables, much faster. Yeah, so looking at these Waymo results really drives home the point. 3DGUT successfully extends Gaussian splatting to handle those difficult distorted cameras and even secondary effects like reflections, giving results close to ray tracing quality, but, well, significantly faster. This is a neat step forward for generating realistic views quickly in AI, especially for real-world captures. Okay, that's about all the time we have for today. Thanks for joining me on the AI Research Roundup. I'm your host, Alex.